Hello everyone, my name is Yeonwook Jung, a first year master's student in the mathematics department at San Francisco State University. Today I'm very grateful to have this opportunity to participate in CSU research competition. Today I'm going to talk about universal patterns in measure theory, specifically a conjecture called error similarity conjecture. I'll start the motivation with some examples. Imagine we have a flat surface here with a line segment on it. If I have another point, this red point, on somewhere else in this plane, can I translate this point? In other words, can I move this point around so that it will lie on top of this line segment? The answer is yes, because I can move this to the right and put it on the line segment. What if I have 2 points? Can I translate these set of 2 points to put on this line segment? The answer is no, because I would have to rotate it so that it will be parallel, and then I can translate on top of this line segment. So I'm going to use 2 operations here. One is translation, another one is rotation. What if I'm given these 2 points that are now further away from each other? Can I rotate and translate so that it will fit on this line segment? The answer is no, because I would have to shrink it in order for it to fit inside in this line segment. So now I'm going to use 3 operations, and that's the operation that I'm going to use today. Translation, rotation, and shrinking. Now let us consider more complicated shapes. What if you're given a 3 point set of 3 points that resemble a triangle? Can I use the 3 operations to put it inside or on top of this line segment? The answer is no. No matter how I translate, rotate, or shrink it, these 3 points will form a triangle that has positive area. And a line segment does not have an area in 2 dimensions. Therefore, we cannot put these 3 points on top of the line segment. Okay, how about if we consider a shape, replace the line segment with the shape A that would possibly have positive area? Can we now put the 3 points inside the shape A? The answer is yes. Since the shape A has positive area, we can shrink this as much as we want, and then when it's small enough, we can put it inside. This logic can be applied to 4 points, 5 points, 6 points, 7 points, 100 points, any number of large points. We can all shrink and put it inside the set A or the shape A that has positive area. In mathematics, a set on a plane is any collection of points. So all 2 points, 3 points, they all form a set. A measure is a formalization and generalization of the usual geometrical quantities such as length, area, and volume, as well as other common notions such as mass and probability. In 1920s, mathematicians were able to show that every finite set can be put into every positive measure set having positive area using the 3 operations that we used. We call these sets universal. So in short, we have that every finite set is universal. We will keep a summary table here, where for finite sets, we'll put a green check because they're universal. We can put them inside all positive measure sets. But the question remains, if finite sets get a green check, what about infinite sets that have infinite number of points? This made one of the most famous mathematicians called Paul Ehrlich consider the following conjecture in 1974. His conjecture is simply this, that no infinite set can be universal. So in our summary table, all here should get a red X mark because they're not universal. Now, in order to answer and prove this conjecture, we would have to consider all sorts of positive measure sets. So I'm going to consider one of the most bizarre and strange sets that will still have a positive measure. One of them is called Sierpinski carpet. I'm going to construct a Sierpinski carpet. Take this square, divide it into 9 equal parts, keep the remaining 8 parts, and remove the central part. For each of the remaining 8 parts, divide again, but this time into smaller pieces, and then also remove the central part again. Do that again for the remaining parts and remove. Do that again, indefinitely. This will give us what was initially a square with infinitely and infinitely many holes. This is called the Sierpinski carpet. We can ask a similar question. Since we want to check if infinite sets are universal or not, take this red triangle that has infinite number of points inside. Can we put this infinite set triangle inside this Sierpinski carpet using the three operations that I initially used? The answer is actually no. And the reason is, if we were to able to put this on top inside the Sierpinski carpet, since this red triangle has a connected part, but note that Sierpinski carpet by construction has infinitely many holes. Therefore, it wouldn't be able to put in anywhere inside this carpet. We call a set with connected parts, for example, this triangle, connected sets. A set that does not have connected parts, for example, this Sierpinski carpet, are called disconnected sets. Mathematicians were able to show that any connected sets are not universal because we cannot put them in disconnected sets. Therefore, in our summary table, for infinite sets, we can say that connected infinite sets, they get a red cross mark. But note that there are still many disconnected infinite sets. We have to put all the X marks in order to prove the Erdős conjecture. But how can we consider, or how can we answer for these disconnected sets? Since they don't have any connected components, it's very hard to measure anything about them. Here is where we need a different perspective. We are going to use something that will, an idea that resembles the notion of density. A mathematician named Newhouse was able to define in 1979 a new notion called thickness for disconnected sets, which are defined by this equation. For instance, in one dimension, you would have a one-dimensional carpet that can be very thick or that can be very thin. He also proved a complementary gap law, which says that a thicker set cannot fit inside a thinner set in one dimension. Based on these theorems, my advisor, Dr. Lai, was able to show in last year that in one dimension, any disconnected set, not only carpets, with positive thickness are not universal. They cannot be put in all positive measure sets. Therefore, he was able to put a red mark for disconnected sets that have positive thickness. But then we have the question, what about for dimensions other than one? What about in planes? What about in 3 dimensions? The limitation is that Newhouse thickness was only defined in 1 dimension, and no one was able to easily generalize this to higher dimensions. Luckily, a mathematician named Yavikoli was able to generalize this notion into higher dimensions using this equation. For example, we would have a thick Sierpinski carpet or a thin Sierpinski carpet. She was also able to prove a complementary lemma, which shows that thicker ones cannot be put in thinner ones in any dimension, not only in 1 dimension. Based on this result, we were able to show that any disconnected set with any positive thickness in any dimension are all not universal. So we were able to prove red X mark here too. But we have one limitation. This argument with thickness cannot answer about the universality of thick sets with 0 thickness. To remedy this part, we were able to define a new concept to our surprise, which we call context sequences, defined by this equation. We were also able to prove a theorem which says that when we calculate the context sequence, if it's non-negative, then one set cannot fit inside another set. Note that the distinguished part here is that it does not talk about thickness at all. So this can be applied to 0 thickness sets too. This relates to our current work, which is in progress for proving that they are non-universal for 0 thickness sets too. So this brings us to the first circle. We were able to prove put all x's here, as well as new results that we are in progress to apply this to prove this conjecture. Our future research directions are twofold. One is that there is a small caveat in higher dimension, where written here, because in higher dimension we can also have stretching in various directions. And another one is to use our new definition and theorems to complete the proof for 0 thickness sets. I want to end this talk by talking about the goal and impact of this research. Error similar conjecture talks about the universal patterns that can exist in measure theory. And measure theory serves as a foundation for various areas of research, especially in differential equations and probability theory. And these are the core areas of research in a broader field of mathematical analysis. Therefore, our goal is to prove this error similar conjecture and ultimately further understand the universal properties in the field of measure theory. Thank you so much.
For your presentation, we're going to go ahead and open it to our judges for their Q&A.
My first question is, I was just a little, I mean, very clear presentation, but I was a little unclear on what specific tasks you did. Like you described, you put in context what other people were doing and how it fit into the bigger picture.
Mm-hmm.
But I was curious specifically what you were doing, what your contribution, what your day-to-day is in terms of this project. Like what are you actually, the actual tasks that you were doing?
That's a really great question. I want to go back to this page. This is what this was the input of my research. So what this says is a thicker set cannot be put in a thinner set. In order to put an X mark here, so I would say putting this X mark was our core work. There was X mark here, but generalizing this to higher dimension was our work. And I did that using the previous theorem, which says thicker ones cannot be put in thinner ones. In order to put X mark here, what I have to do is, if anyone gives me any disconnected set, I have to find a positive measure set that this cannot go in. I have a tool that can say when that can happen, when one cannot go in, because thicker set cannot get in a thinner set. But I have to show that no matter who gives me which kind of disconnected set, I'm able to construct a set that this won't go in. Therefore, it's not going to be a universal pattern. And finding that set is as hard. Can be very difficult because someone can come up with very crazy looking like disconnected sets. And I should be able to take account for any possible disconnected set. In one dimension, it's more simpler, but my main work was to generalize that same work in the language of higher dimension, but using this new definition of Yeonwook Jung.
So I'm just because I mean I'm a astrophysicist. I'm used to working with data, and I can, I have tools that I use to analyze my data. So, but mathematical research is fascinating to me because I'm just curious about your day to day. Like, are you sitting in front of a computer? Are you actually? Do you have some computer program that like, oh, look at this pattern, let me try some rotations and stretches and this, and I try to translate it? Like, how are you going about your day-to-day in your research?
So it mostly happens with coffee and pen and paper. I sit down, I write down this definition. I write down the definition for disconnected sets. It can be written down in mathematical symbols and languages. How can I deduce from this equation in logical steps so that I'll come to the conclusion about disconnected sets? So what I usually do is I write down all possible assumptions that I have to deal with. And I also write down where I have to end as a destination. And using logical steps in mathematical deduction, like theorems and lemmas and other things, guided by inspiration given by examples, what kind of steps do I have to take in order to write down the proof so that I'll get into that place? So I do not use computer. I never use computer in this research, but there were a lot of drawings on board because symbols are easily made, we can imagine them easily with drawings and so on. Yes, and Sierpinski carpet, those things are also very informative because by looking at them, we can get insights on what kind of proofs we have to come up when we're dealing with these abstract notions of connected, disconnected, and thickness, and so on. Thank you.
Okay, my question comes from your paper.
Mhm.
You talk about patterns. I really loved your first paragraph talking about different kinds of patterns.
Mhm.
But I don't understand how this research is related to like this idea of universal or not universal patterns.
Mhm. So this, we're trying to find if there is, we're trying to answer the question if there is a universal, if there is a set, if there is a set that would be, that we can put inside any positive measure sets. So there can be, there's just so many positive measure sets, starting from simple geometrical structures, which can also, to some very weird shapes of geometrical structures. But would there exist a common thing that we will always be able to find for any of those sets? In other words, we can also apply it in reverse and use it in the other way. If I want to show that something has no measure, then what I have to do is show that this pattern will not exist. Because every set that has positive area and volume will inevitably contain this pattern. So if for some reason this was prohibited, then no matter how complex the data or function or whatever it looks like, its area in the end will be zero.
Okay. So you're saying that like finding something that's similar about all the sets is like finding a pattern.
Yes.
Okay. And I had the same question as Professor Barranco about your paper, in that I wanted to know like which part of it you wrote and which part of it came from something that had already been published.
Mm-hmm.
But it will be hard to tell me that right now. I just think that going forward, as you make your slides, it would be useful to be very clear, like these people already published that and this is what I'm using, this is what I have used to advance the theorem forward.
Mm-hmm.
And I don't know if we have time, but I'm curious about like when you go to your little checkbox thing.
Yes.
Like I didn't understand what this except rotation and stretching means. So like you proved it for translation, but not rotation and stretching yet?
That's almost exactly right. So in one dimension, everything is pretty simple. One reason it's simple is because I started to say that there was 3 operations we can do, just translation, rotation, and shrinking. But in one dimension, we can't rotate something because there's no space to do it. That's why, although it was very hard, because it was only proven last year, but one dimension is quite special because we only have to care about only 2 directions. But in higher dimension, not only rotation, there can be shear transformation, which is if you have a square, we can squish it down. And those things was not considered at all. And we were able to replicate, we were able to do the same shrinking and translation for this work. But rotation and
Okay.
shear, we have to also take account and complete the proof.
Mm-hmm. Okay.
Okay, any additional questions, comments? Okay, awesome, great presentation. Thank you so much.